Welcome back, friends. So today we are going to discuss one more algorithm. And in the previous video, I discussed you about this one. Find if a binary tree is binary search tree. You can go there and see that what approach I have used. I have used the stack there, right, to find out if a binary tree is a binary search tree, right? So today's algorithm is if we have to find out if we have given two binary search trees and we have to find out that if both the binary search trees contain the same set of elements or not. So in that case, what we will do? So the same kind of approach of using a stack, I'm also going to follow here, right? So let's go to the code. So here I have written the code beforehand so that I can save some time because I just need to explain you the logic. So here I have two arrays. This array is like this and this array is like this. So both the arrays have same set of elements, but both the arrays have those elements in some other order, right? So if you will create the BST using this array or this array, they may contain the different structure. Both the binary search trees may have the different structure, but ultimately they will contain the same set of elements, right? So before that, I would like to show you something. So I'm just going to write one in order function. Just need to copy from here. I'm just going to write one in order function to show you something. So in order traversal, just remove it, and here just you need to do like this, and here I'm just going to print the value. So it's like p root to n data. Okay, so this is the in order traversal logic. This is the function, and if I do the in order traversal, suppose for say I'm just going to comment this for some time, and here I'm going to do an in order traversal of this binary search tree which has been represented by root 1. So here I have written the logic to create two binary search trees, one rooted at p root and the other rooted at p root 2, right? P root 1 and p root 2. So here I'm just going to give you the in order traversal of p root 1, right? So if you see that you're already aware that this in order traversal will give you all the elements in the binary search tree in the sorted order, and that sorted order will be from smallest to biggest, right, in the increasing order. So 1 is the smallest and the 25 is the biggest, right? Suppose if I have to just print these elements in the in order traversal in the reverse sorted order, then what I will do? I hope you got the point, and I hope you guess like what I need to do. I just need to do like p right here and p left here, right? If I do this, then now if I run this, then all the elements in the first binary search tree that I'm using, they will be shown in the reverse sorted order, means the decreasing order, right? So you can see that 25 is the first element and 1 is the last element, right? So I have told you this thing because our logic to find out if both the binary search trees have the same set of elements will follow the same thing, that is based on the same kind of logic, right? So let's see what I have done. Just need to remove this. There is no use of this. Just need to uncomment these two. So you can see that here I have created first binary search tree. This insert node, you already know that this is the function which is adding the nodes to the binary search tree. And then what I'm doing, I'm again creating the second binary search tree using p root 2, so which is rooted at p root 2. And then I'm just calling this function. Both have same set of node values and passing the roots of both the trees, p root 1 and p root 2, right? So let's go to this function because this function contains the actual logic. So let's go to the both have same set of node values. So this is the first tree and this is the second binary search tree. So what I'm doing, I'm taking this first binary search tree and I'm just putting all the values in the stack in the in order traversal, right? Why in the in order traversal? Because in the in order traversal I will get all the elements stored in the stack in the sorted order. So if all the elements will be stored in the stack in the sorted order, then what will be the order? what they will look like. Suppose I have 1 2 3 4 and 5, these are the elements. So if I will do storage, then if I will store this in stack, then what will be the case? This will be the case. The greatest element will be at the top and the smallest element will be at the bottom. This is the stack, right? So same thing will happen here. All these things will be stored, all these values will be stored in the stack in the reverse sorted order. The top element will be the greatest element, because when I will just start traversing the stack, then I will find the greatest element at the top of the stack, right? So that is why I am traversing it in the in order traversal. In the same manner you traverse in the in order traversal, so it's left, then root, then right. So when I'm traversing the root, then rather than displaying it on the screen, I'm just putting it into the stack. This is the stack, sttemp. This is my stack. This I have taken. This is a STL stack, standard template library I'm using. For this, you need to include this one, hash include stack. So I'm using this one. You can create your own stack. There is no problem with that one, but that should contain the correct logic, right? It should be able to do the correct things, right? So here is the stack where I'm just putting all the elements in the in order traversal. So when I will put all them in the in order traversal, then what will happen? The stack will contain the greatest element at the top and the smallest element at the bottom, right? Now, what I'm doing, I'm calling this function stack has same node, right? Stack has same nodes. This is the function which I have written here. Stack has same nodes. So what I'm doing here, I am passing the p root 2 here, the second binary search tree root. I'm passing the second binary search tree root here. And what I'm doing here, first you need to check here in the else part. So here what I'm doing, I'm just doing the reverse, right? Right, root and left. For the root element, I have written the logic, because root element need to be, when I will be visiting the correct element in the traversal, then I need to just find out if my element is same as the topmost element of the stack or not, right? Because I am going in the reverse order, right? So when I'm going to the reverse order, then what I'm doing, I'm checking, I'm testing whether the data at the root node, it's same as the topmost element of the stack, right? If it is the same as the topmost element of the stack, I'm doing nothing. I'm just popping it. I'm just getting the element popped from the top so that I can compare the second element in the next visit, right? So I'm just following this, and this logic is just the reverse of the in order traversal, so that all the elements have been traversed in the reverse order, in the decreasing order. Because if you go to this one, here I have written like 5 4 3 2 1. So you created a stack and all these elements were stored on the stack, but this element will be at the top, which is the greatest element. And now in this function, stack has same nodes. What I'm doing, I'm also doing the same. I'm just going in the reverse order, so that the topmost element will be the greatest and the bottommost element will be the smallest. And with each iteration, with each visit of the node, I'm just comparing it with the topmost node of the stack. If the topmost node of the stack and whatever node I have visited, if both of them have the same value, then we are fine. But if at some point I found that no, my element is not matching with the element with the top element of the stack, then in that case it means that both the binary search tree doesn't have the same set of elements, right? So this is actually the logic which will work here, right? So if at some point of time, if I found that my stack, the top element of the stack is not the same element as the node I have visited, then in that case what I will do, I will mark this be it same as false, and I will just return from here. And then when I will when this function will be called, then this will do the rest of the things, because then it will not go into any more iterations. I mean, it will not put any more calls in the recursive call stack, right? So this is the whole logic. I hope you got the point what I'm doing here, and why I showed you in the beginning of this video that what is the meaning of in order traversal in the reverse order, right? So this is the way using which I will be finding out if my arrays, which represents two binary search trees, they have the same set of elements or not. Okay. So what I need to do here, I just need to run this now. So here I have both the arrays having the same elements, and I have created two binary search trees, p root 1 and p root 2, and then I have just checked whether both the binary search trees have the same set of values, same set of nodes, and then I have printed this bh same, right? Because all the logic has been executed inside this function. So if both the trees doesn't contain the same set of element, then this will be false. Otherwise, it will be true. True means 1. So here in this test case, what is happening? Like here, I don't have any element which is not available in both the arrays. Their order may be different, but they are available in both the arrays. So the trees created using these two arrays, they may contain the different structure, but ultimately they both have the same set of elements, and that is what we have asked to find, whether they have the same set of elements or not, right? So let's see, in this case it should come as 1, right? So our output should be 1. It should be true, so it should be 1. So here you go, this is 1, right? Now I just need to do one thing, I need to make it 13. Now do we have both the arrays same elements? No, both the arrays don't have same elements, so both the binary search trees will also not have the same set of elements. So in this case, this should return false. So let's see what comes out to be. Okay, so you found it out, it's 0, right? So our algorithm is working fine. So you can do one more thing, like while you will write your own code, then you can do something like that. You can just add one more element here, and at the end you can just add 30, and then just here you can do like 10, and then just create it. And in this case as well, you should be able to find it out, like our binary search trees are not same. So you can try various other combinations of your testing during your testing, and you will be find that this algorithm is working fine, right? So you can see, you can think of other approaches as well to find it out whether the two trees have the same set of elements, but I found personally this approach very useful, right? Basically this approach is useful for binary tree and binary search tree both, right? So there were other approaches as well which I have studied about them in on the internet, and they were saying like first iterate the first do the in order traversal or any order traversal of the first binary search tree, then do the traversal of second binary search tree, and then compare the elements which you have traversed, right? So basically they were trying to say like you just traverse the first binary search tree and store all the elements in an array or a vector, and then you traverse the second binary search tree and store all the elements in the second array or the second vector, and then compare both the vectors, and both the vectors should have the same values at the same index, right? So what was happening in that case, you have to do 3 iterations, but here in only 2 iterations you are able to do the things, right? Because there you will do first iteration first in order traversal, then you will do the second in order traversal, then you will iterate through the vectors, right, to find out if both are same or not, both the vectors contain the same set of values or not, right? But here what we are doing, we are able to find it out only in 2 iterations, and that iteration is also only the traversal of the binary search tree. First binary search tree we need to traverse in the in order traversal and store all the elements in this stack, and then you need to traverse the second binary search tree in the reverse order traversal, in the in order traversal manner, right? So that way in only 2 iterations we were able to find it out if both the binary search tree contains same set of elements or not. And believe me, this logic, this use of a stack, you can find it very useful in many other algorithms as well, right? It's not only helping you to find it out the solution of these kind of problems, you can think of other algorithms as well where you can use the stack approach, right? So that was all for today, and in the next video I will try to explain some other algorithm before I implement something. Since this was using the same logic as this one, find if a binary tree is binary search tree, so I just made this video in the continuation of the previous video. right? So I hope you got this video useful, and this will be useful for you to solve other algorithms as well. So I hope you are getting good things here on my channel. So please like, subscribe my channel, and please share the videos with your friends, and let me know if you want to know something else, if you want me to cover few other things in on our channel, so that we can improve it more. Our target is to fill the gap for the students, basically for the students. Whether you are a professional or you are a student, you can visit this channel, but ultimately this channel is targeting the students. Why this is targeting the students? Because the students don't have the live exposure of those many projects, right? So what is happening in the industry, how they use various concepts like file handling or data structures, how they use it, right? Those kind of things, and what kind of algorithms they implement, those kind of things they should be aware of, right? So that is why this platform is going to fill that gap, and that is the purpose of creating this Varteta learning platform video channel on the YouTube, right? Okay guys, so have a nice day, bye bye, and we'll meet soon with some other interesting algorithms. Till then, have a nice day, bye bye, and take care.